2.3.4 Rotor field excitation. They're saying the rotor must be excited from an external DC source. But if full resistance is applied to the rotor field circuit, then the field strength of the rotor is at a minimum, the power factor is extremely lagging. As the DC field strength is increased, the power factor improves. If current is increased sufficiently, the power factor can be increased to near unity or 100%. By increasing the rotor field strength further, the power factor decreases, but in a leading direction. You can actually get this thing to be capacitive rather than inductive. This means that the stator circuit becomes capacitive and the motor is said to be overexcited. Synchronous motor can be used to counter the lagging power factor by adding capacitive reactive circuit, bringing the overall power factor closer to unity. It says if the rotor DC field winding of a synchronous motor are open when the stator is energized, a high AC voltage will be induced in it because the rotating field sweeps through a large number of turns at synchronous speed. It can be at dangerous levels. It says it's necessary to connect a low value resistor across the rotor DC field windings during the starting period. So what they'll actually do is, and they're not going to put DC in this. What they're going to do is hook it up to an external resistive bank resistor. So they have low value resistors in here, and it just shunts this and allows it to become an induction motor on startup. Once it starts turning and you get to near synchronous speed, they'll disconnect those resistors and they'll connect it to the DC source. It says it's necessary to connect a low-value resistor across the DC field winding during the starting period. During the starting period, the DC winding is disconnected from the source and the resistor is connected across the field terminals. This permits the AC to flow in the DC windings. Because the impedance of the winding is high compared with the inserted external resistance, the internal voltage drop limits the terminal voltage to a safe value. And then when the synchronous motor becomes asynchronous, it's connected, it is said to be out of step. This occurs when the following takes place singly or in combination. Excessive load is applied to the shaft, or supply voltage excessively reduced, or the motor excitation is lost or too low. You can actually get out of step. Torque pulsations applied to the shaft of a synchronous motor are also a possible cause of loss of synchronism. If the pulsations occur at an unfavorable period relative to the natural frequency of the rotor with respect to the power system. They're almost talking about harmonics in a way. A prevalent cause of loss of synchronism is a fault occurring on the power supply system. Under excitation of the rotor is also a distinct possibility. Synchronous motor pull-out is significant in that the squirrel cage or amortisseur winding is designed for starting only. Therefore, if it is not as hardy as those found in induction motors, the amortisseur winding will not overheat if the motor starts, accelerates, and reacts synchronous speed or reaches synchronous speed within a time interval determined by the normal for the motor. However, the motor must continue to operate at synchronous speed. If the motor operates at a speed less than synchronous, or if it gets out of step, the amortisseur winding may overheat and suffer damage. So protection against a synchronous motor losing synchronism can be provided by a polarized field frequency relay or out-of-step relay, as well as various digital methods. Synchronous motor torque angle. When the rotor is brought up to high speed, it'll lock onto the rotating magnetic field. Under these conditions, running torque will be developed. The rotor will rotate at synchronous speed in a direction and at a speed determined by the synchronous speed. While motor is running, the two rotating fields will line up perfectly. The rotor pole will always be lag behind the stator pole by some angle. This angle is called the torque angle. So it says as the load of the shaft increases, the torque angle increases even though the rotor continues to turn at synchronous speed. This behavior continues until the torque angle is approximately 90 degrees. At that point, the motor develops maximum torque. Any further increase in load will cause one of the following to occur. If the increase in load is momentary or very small, the rotor will slip a pole. In other words, the stator field will lose hold of the rotor and grab onto it again the next time around. If the increase in load is large enough and is not momentary, the motor will lose synchronism and will either stall or cause the rotor to suffer thermal damage. In both cases, a noticeable straining sound will be heard. So a synchronous motor should not be used in applications where fluctuations in torque are violent. As a rule, the synchronous motor is also not used in small sizes under 50 horsepower because it requires DC excitation. It's more difficult to start than induction motors and falls out of step readily when the system disturbances occur. Common applications for synchronous motors are in motor generator sets, air compressors, and refrigerating plants. Single phase induction motors. We're going to talk about a starting winding because we're going to have to tell the rotor which way to turn. Although single phase motors are easier to manufacture in small sizes and are less expensive than three-phase motors, they can't do the same work without using much larger conductors to carry larger currents. Examples of many applications for single phase AC motors today are refrigerators, washers, dryers, power tools, and HVACR systems. Single-phase induction motors. Single-phase AC induction motors are extremely common. Unlike polyphase induction motors, the stator field in the single-phase motor does not rotate. Instead, it simply alternates polarity between poles as the AC voltage changes polarity. So those north-souths are just, they're not rotating, they're just changing north-south, 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 north-south. Much like the compass at the beginning of the explanation where I said if you had two north poles and you had a compass, you could cause that compass to move by hammering alternately those north poles beside the compass. You can get that needle to turn clockwise, you can get it to turn counterclockwise. That's the same with these single-phase induction motors. They can turn backwards, so they need some way of knowing which way to turn. That's called a starting winding. So voltage is induced in the rotor and a magnetic field produces around the rotor. This field will always oppose the stator field. However, the interaction between the rotor and the stator fields will not produce rotation because this forces across the rotor and through the pole pieces. There's no rotary motion, just a push and or pull along this line. So if the rotor is rotated by some outside force, a twist of your hand, for example, the push-pull along the line is disturbed. Look at the field shown in figure 38. As the motor begins to rotate at that instant, the south pole on the rotor is attracted to the left-hand pole. The north rotor pole is attracted to the right-hand pole. All of this is a result of the rotor being rotated 90 degrees by the outside force. So, split-phase induction motors. The split-phase motor shown schematically in figure 39 has a stator composed of a slotted laminations that contain an auxiliary starting winding and a running main winding. The axes of these two windings are displaced by an angle of 90 degrees. So you can show this motor a north and north and then a south and a south, and it'll actually cause this rotor to rotate. It tells the rotor which way it needs to go. And once you get close to synchronous speed, then this centrifugal switch will open. You no longer need this starting winding. So you can make this starting winding out of very fine wire that has high resistance. So it has a higher resistance compared to its inductive reactance, where the main winding is a thicker wire, so it has lower resistance as compared to the inductive reactance. You can use many turns in the main winding, increasing the inductive reactance. So you can make that phase angle greater. You can use fewer turns in the starting winding. So fewer turns is lower inductive reactance, and a thinner wire is higher resistance. you can make this side more resistive than this main winding. But because it's using thin wire, you can't leave it in while the motor runs. So when you get up to 80% or so of running speed, this centrifugal switch will open and disconnect the starting winding. Starting winding has fewer turns and smaller wire than the running winding, therefore has different electrical characteristics. The main winding occupies the lower half of the slots and the starting winding occupies the upper half. The two windings are connected in parallel across the single-phase line supplying the motor. The motor derives its name from the action of the stator during the starting period. When energized with single-phase AC, the two windings are physically different enough to position and in position and construction to produce a revolving magnetic field that rotates around the stator air gap at the synchronous speed. As the rotating field moves around the air gap, it cuts across the rotor conductors and induces a voltage in them. The interaction between the rotor and the stator causes the rotor to accelerate in the direction in which the stator's field is rotating. When the rotor has become to about 75% of synchronous speed, a centrifugally operated switch disconnects the starting winding from the power source, and the motor continues to run on just the main winding. So, there you go. If the motor draws the high starting current for more than 5 or 10 seconds, the relay will de-energize the motor so you don't burn up that starting winding. In a split-phase motor, the starting torque is 150 to 200% of the full load torque. The starting current is about 6 to 8 times greater than the full load current. Fractional horsepower split-phase motors are used in a variety of devices such as washers, oil burners, ventilating fans. The direction of rotation of a split-phase motor can be reversed by interchanging the starting winding leads. Okay. So here's a little split-phase motor, and here's that centrifugal switch. When it spins fast enough, these two weights are thrown away from each other, and you disconnect that switch. You take off you open the starting winding. So, and here's a good example of the stator. See, this is showing you these thicker wires. This is the running wire. These thinner wires. This is the starting wire, starting winding. Excuse me, starting winding and the running winding. We can use other ways to split those phases. We can use other ways to create an angle of attack, and a capacitor is one type. Capacitor type motor is a modified form of the split phase motor. The capacitor is located on the top of the motor. So whenever you see a motor with a big bubble on the side, that's housing the capacitor. Sometimes it's a capacitor start motor, sometimes it's a capacitor run motor, sometimes it's a capacitor start run. It might have two capacitors, and the starting capacitor is taken out of the circuit, but the running capacitor remains in the circuit. To develop a larger starting torque than that available with the standard split-phase motor, a capacitor is placed in series with the auxiliary winding of a split-phase motor. This is called a capacitor start motor, and it's the most common form of capacitor motors. Again, they have a centrifugal switch, so when we get up to 75 to 80% of running speed, we're going to take the starting winding and that starting capacitor out of the circuit. The capacitor tends to create a greater electrical phase separation of the two windings. Because the reactance of a capacitor is 180 degrees out of phase with the inductive reactance of the motor, windings, when they're combined, they yield a lower total impedance. This allows a larger current to produce a greater magnetic field. The net effect of the capacitor is to give the motor a starting torque of about 4 times its rated torque. The split-phase motor, on the other hand, produces a starting torque of about 1 to 2 times its rated torque. When the capacitor motor has come up to speed and the starting winding has been disconnected, it will have the same running characteristics as the split-phase motor. So, to reverse the direction of rotation of the capacitor start motor and the split-phase motor, the connection of either winding must be reversed, but not both of them. Because the starting winding is disconnected at the high speed, This reversal can be accomplished only at standstill or low speeds when the centrifugal switch is still closed. All right. Capacitor start motors are made in sizes from 1/4 horsepower up to 10 horsepower. Starting capacitor is the dry type electrolytic capacitor made from AC for AC use. Typical values from 200 to 600 microfarads. Shows a comparison. Figure 42 shows a comparison of torque slip curves for a split phase capacitor. All right, let me keep going here. A variation of the capacitor start motor is one in which the capacitor and auxiliary winding are not disconnected. The centrifugal switch is eliminated and the auxiliary winding remains energized after startup. So that start winding has to be made out of thicker wire. This motor is called a capacitor run motor. The capacitor used for continuous operation is not the same as that needed for starting. Start capacitors cannot be used as run capacitors. Result of the change is that the motor has improved running characteristics. However, a run capacitor does not provide as much starting torque as a start capacitor. Among the improvements are higher efficiency and power factor at rated load, lower line current, quieter operation. It should also be pointed out that the start winding must be designed for continuous operation. Motor designed for use with a start capacitor shouldn't be rewired to operate with a run capacitor only. So, another variation of the capacitor start, capacitor run motor. This motor combines the useful features of the capacitor start and the capacitor run motors by using two different capacitors. There you go. So here's the run capacitor. It's in series with this main winding. And here are your start capacitors and the centrifugal switch that's going to disconnect it. Shaded pole induction motors. A shaded pole motor employs a salient pole stator and a cage rotor. The projecting poles on the stator resemble those of DC motors, except that the entire magnetic circuit is laminated, and a portion of each pole is split to accommodate a short-circuited copper strap called a shading coil. So it's just a small little, it's like one wrap or two wraps, and that shading coil also tells the rotor which way to rotate because it's going to have a different electrical characteristic than the main coil. They use the same wire, they just go one little wrap around that shading coil and then they go around the rest of the coil. So, shaded pole motor employs a salient pole stator and a cage rotor. The projecting poles on the stator resemble those of DC motors, except that the entire magnetic circuit is laminated, and a portion of each pole is split to accommodate a short-circuited copper strap called a shading coil. This motor is manufactured in small sizes up to about a 20th of horsepower. A 4-pole shaded pole motor is illustrated in figure 44. The shading coils are placed around the leading pole tip, and the main pole winding is concentrated at and wound around the entire pole. The 4 coils that make up the main winding are connected in series across the motor terminals. So they'll use these for very small motors like an exhaust fan in the bathroom. That would use a shading pole motor. They're very small, they're very inexpensive. For their relative size, they're very noisy. So figure 45 shows that during part of the cycle when the main pole flux is increasing, the shading coil is cut by the flux and the resulting induced EMF and current in the shading coil tend to prevent the flux from rising readily through it. Thus, the greater portion of the flux rises in the portion of the pole that is not in the vicinity of the shading coil. When the flux reaches its maximum value, the rate of change of flux is 0 and the voltage and current in the shading coil are also at 0. At this time, the flux is distributed more uniformly over the entire pole face. As the main flux decreases towards 0, the induced voltage and current in the shading coil reverse their polarity. Resulting force tends to prevent the flux from collapsing through the iron in the region of the shading coil. The result is that the main flux rises first in the unshaded portion of the pole and later in the shaded portion. This action is equivalent to a sweeping movement of the field across the pole face in the direction of the shaded pole. Cage rotor conductors are cut by this moving field, and the force exerted on them causes the rotor to turn in the direction of the sweeping field. So it's almost like it has a little electronic brake on it. Most shaded poles have only one edge of the pole split. Therefore, the direction of rotation is not reversible. However, some shaded pole motors have both leading and trailing pole tips split to accommodate shading coils. The leading pole tip shading coils from one series group and the trailing pole tip shading coils from another series group. Only the shading coils in one group are simultaneously active, while those in the other group are on an open circuit. All right. So here's your capacitor start capacitor run motor. It's got two capacitors. Capacitor start capacitor run motors run quietly and smoothly and have a high starting torque. Their construction is similar to a split phase motor in that they use a centrifugal switch to remove only the start capacitor from the starting winding while leaving the run capacitor connected to the winding. These motors have a higher power factor than ordinary split phase motors. (2.4.5) Synchronous, single-phase synchronous motors. Single-phase synchronous motor, as its name implies, runs at synchronous speed. It finds use where a constant speed is needed, such as in tape recorders and clocks. It started in the same way as any of the single-phase induction motors, and therefore has a rotating field. By having a modified rotor, the motor pulls into synchronism and runs at synchronous speed. Multiple speed induction motors. Here's a highlight. It says the speed of an induction motor depends on the power of the supply frequency and the number of pairs of poles used in the motor. Thus, to alter the motor speed, it's merely necessary to change one of these two factors. By far the most common method involves changing the number of poles. Generally, though, some type of external controller or even manually changing the wiring connections. There are two types of multi-speed squirrel cage induction motors: multiple winding motor. In a multiple winding motor, two or more separate windings are placed in the stator core slots, one over the other. For example, a 4-pole winding can be positioned in the core slots and have a 2-pole winding placed on top of it. Windings are insulated from each other and arranged so that only one winding at a time can be energized. Switching speeds is normally accomplished by switching contacts that are in the motor controller external to the motor itself. So either you're using all 4 poles or you're only using 2 poles. Consequent pole motor. Consequent pole motors have a single winding with 2 speeds. Motors constructed to have a certain number of poles for high speed operation, and by switching action doubles this number of poles for low speed operation. Switching action is shown in figure 47. If you trace the wiring, you can see how both magnetic north and south poles are produced at the winding projections. With power applied to the 2-pole motor, a rotating magnetic field at 3600 RPM is produced. So you come in, you go through this south, through this other south, back to B. B comes through north and north, back to line 2. So if you wanted to, you could disconnect either line 1 or line 2, and you'd only have 2 poles rather than having 4 poles. Figure 48, the connections are changed so that the system produces 4 magnetic poles at the winding projections. Because every north pole must have a south pole, consequent south poles are produced between the projecting north poles. So here we've changed all 4 of these into north poles. And they're saying that you get a subsequent south pole. It's kind of a phantom pole in between the norths. So you can go from a north-south, north-south to having 4-pole. Figure 49 shows the short jumper arrangement of a consequent pole motor. All windings are in series and alternate north and south poles are produced. To produce consequent poles, the series connection is replaced with a parallel connection accomplished by the long jumper arrangement. By connecting the motor in this manner, 4 alignment poles are produced and as a result create 4 opposite consequent poles. In the practical consequent pole motor, all necessary internal connections or rearrangements are accomplished at an external control panel. So there again, you've got the north-south, north-south arrangement, and by changing it to parallel, you can change all 4 of those into north, and then you get these phantom south poles. Here's a highlight. It says that a consequent pole motor or a constant torque motor horsepower varies directly with speed. It's used to drive pumps and air compressors as well as in constant pressure blowers. So a constant torque motor, the horsepower varies directly with the speed. Section 2 review. The motor has 4 poles and is operating at a frequency of 60 hertz. The synchronous speed is, remember your formula, 120 times frequency divided by poles. A type of motor most likely to be used in location with flammable dust and torque fluctuations. All right, I'll let you look at that. A type of motor used in precision application that requires constant speed with 0 slip. And a heating system is most likely to use what? All right. 3.0.0, variable speed drives. 3.0.0, variable speed drives. Identify types of adjustable speed loads, identify types of motor speed controls, and identify braking methods. The need for speed control in industrial equipment is increasing due to the need for better production control and for energy savings, where less power is required. AC drives compete with DC drives, eddy current drives, and mechanical and hydraulic systems as methods to control speed. Reliability, cost, and control capabilities are the major factors in system selection. Adjustable speed loads. Most drive controllers can be adjusted or modified to optimize performance and provide the most efficient and cost-effective drive, depending on load characteristics of the application. It's important to understand the speed and torque characteristics as well as the maximum horsepower requirements for the type of load to be considered. Based on this, either a constant torque controller or a variable torque controller is selected. Most common types of loads are shown in figure 50. So here we have the torque is constant as the horsepower increases in synchronous with the speed. This is a percent speed of variable torque load. So this is a variable torque and a percent speed of constant horsepower. So the horsepower stays constant even when the speed increases, the torque decreases in order to keep the horsepower constant. For constant torque load, the torque remains constant throughout the speed range and the horsepower increases and decreases in direct proportion to the speed. This applies to applications such as conveyors as well as applications in which shock loads, overloads, or high inertia loads are encountered. A variable torque load requires much lower torque at lower speeds. This applies to applications such as centrifugal fans, pumps, blowers. Constant horsepower load requires high torque at low speeds, low torque at high speeds, and thus constant horsepower at any speed. It applies to applications such as lathes requiring slow speeds for deep cuts and high speeds for finishing. Usually very high starting torques are required. Motor operating in quadrant 1 has a positive torque and speed, which means that they both act in the same direction. The motor in this quadrant functions as a motor and delivers mechanical power to the load. While operating in quadrant 2, a motor will develop a positive torque and a negative speed. The torque is acting clockwise and the speed is counterclockwise. In this quadrant, The motor absorbs mechanical power from the load and functions as a generator. This mechanical power is converted into electric power and is generally transmitted back into the line. The electric power may also be dissipated in an external resistor, which is known as dynamic braking. So here's quadrant 1, speed is increasing. Here, quadrant 2, the torque is increasing. Let's see here, where's quadrant? Okay, depending on its connection, the motor may be used as a brake while operating in quadrant 2. That's that dynamic braking. Absorbed mechanical power is converted into electrical power, then converted into heat. If the motor absorbs electric line power as it converts mechanical power into electric power, it functions as a brake. Both power inputs are dissipated as heat. Sometimes they want to capture that energy, not just transmit it into heat. So in this case, the motor will act like a generator and it'll actually charge up a battery. It'll actually store that power. So it's a power recovery. A lot of your electric cars are like that. As you apply the brakes, it's not really a brake. It turns the motors into generators and it regains that power. So quadrant 4 operations identical to quadrant 2, except that the speed and torque are reversed. Okay. Typical torque speed curve. Three-phase motor has a torque speed curve that's a good example of a motor's behavior as a generator brake. The solid curve is the torque speed curve for a motor in quadrant 1, a brake in quadrant 2, and a generator in quadrant 4. So there you go. That's your torque highlight. If the stator leads are reversed, the torque speed curve is shown by the dotted curve. Now the motor operates as a motor in quadrant 3, a generator in quadrant 2, and a brake in quadrant 4. So here's quadrant 2, it's acting like a generator, it's acting like a motor in quadrant 3, and over here it's acting like a brake. All right, let's move on. Motor heating because of variable speed drive system includes both the drive controller and motor. Design engineers should always consider the capabilities of the motor to perform acceptably under the desired operating conditions. A factor to observe is motor heating. When operating a motor at reduced speed, the ability to dissipate heat is also reduced due to the slower cooling fan speed. This factor should be considered when maintaining the motor, modifying its enclosure or surrounding area, or troubleshooting the drive system. So that motor has a built-in fan. As it runs at full speed, it actually is cooling itself. When you run it at a slower speed, some motors will overheat. So you have to figure out a way to keep it cool. Varying the speed of a DC shunt motor. A DC shunt motor, shown in figure 54A, basically there are two ways of varying the running speed of a DC shunt motor: adjusting the voltage applied to the field winding or adjusting the voltage applied to the armature. So either way, you're adjusting that voltage. So here's a DC shunt. Remember, shunt means parallel. Shunt motor. It has a variable resistor in series with that field winding. And here we can put the variable resistor in series with the armature. It says as the field voltage increases by reducing the rheostat, the field current is increased. This results in a stronger magnetic field, which induces a greater counter-electromotive force in the armature winding. The greater CEMF tends to oppose the applied DC voltage and reduces the armature current. Therefore, an increased field current causes the motor to slow down until the induced counter-electromotive force has returned to near its normal value. So you can actually reduce the amount of resistance in series with this field winding. You can slow the motor down. Going to the other direction, if the field current is reduced, the magnetic field gets weaker. This causes a reduction of the counter-electromotive force created by the rotating armature winding. The current in the armature increases, forcing the motor to spin faster until the counter-electromotive force is once again approximately equal to what it was before. This method of speed control has certain positive features. It can be accomplished by a small and expensive rheostat because the current in the field winding is fairly low. Also because of the low values of the field current and the rheostat voltage does not dissipate very much energy. Therefore, this method is energy efficient. Okay. So where's the second one? From the torque producing point of view, armature control is much better, as shown in figure 54, as the armature voltages and current are increased by reducing the voltage drop across the rheostat. The motor starts running faster, which normally requires more torque. Reason for the rise in speed is that the increased armature voltage demands an increased counter-electromotive force to limit the increase in current through the armature to a reasonable amount. The only way the counter-electromotive force could increase is for the armature winding to spin faster because the magnetic field strength is fixed. So they're saying it's a better way to control this by putting the rheostat in series with the armature rather than with the field winding. Problem with the armature control method is that the voltage drop across the rheostat must handle the current through the armature, which is relatively large. Therefore, the rheostat voltage must be physically large enough and expensive, and it will waste a considerable amount of energy. Varying the speed of an AC motor, the principle of speed control for adjustable frequency drives is based on the following formula. Synchronous speed equals 120 times the frequency divided by the number of poles. The adjustable frequency system controls the frequency applied to the motor. The speed of the motor is then proportional to this applied frequency. Control frequency is adjusted by means of a potentiometer or external signal, depending on the application. Frequency output of the controller is adjustable over its design speed range. Therefore, the speed of the motor is adjusted over the same range. Because an electronic means of generating variable frequencies is being used, the speed range often exceeds the 60 hertz rated speed of the motor. So they actually take the incoming power, there I have a picture of it, they take the incoming power and put it through a rectifier, changing it to DC. Then they can use that DC to approximate through an inverter. They can approximate a sine wave. And the first question is, why would they change AC to DC only to change it back to AC? The reason to do that is because you can change the output frequency, the frequency that's being delivered to the motor. The supply voltage is a constant 60 hertz, but coming out of that variable speed controller, you can make the frequency 0 hertz or 15 hertz or 30 hertz. You can make it 120 hertz. Some of the motors are meant to be overclocked, and you can run them at twice their speed for short periods of time. I think no longer than 5 minutes at a time, but you can run it higher when you need to. So it says if the motor has a nameplate rating of 240 volts at 60 hertz, the voltage to frequency ratio, 240 divided by 60, is 4. If the motor is sped up by adjusting its variable frequency inverter to 90 hertz, the voltage magnitude must be increased to 360 volts. 4 times 90 equals 360. If the motor is slowed down by adjusting the inverter frequency to 45 hertz, the voltage magnitude must be decreased to 180 volts. So you have to keep that ratio of voltage to hertz constant. Stator's magnetic field strength must remain constant under all operating conditions. The stator field strength should happen to rise much above the design value. The motor's core material would go into magnetic saturation. This would effectively lower the core's permeability, preventing proper induction of voltage and current in the rotor loops, and detracting from the torque producing capability of the motor. On the other hand, if the stator field strength should happen to fall much below the design value, a weakened magnetic field would simply induce lower values of voltage and current in the rotor loops. This would also detract from the torque producing ability of the motor. So we need to keep it very close to that ratio. In the equation, XL does not remain constant at the supply frequency as the supply frequency is adjusted, but varies in proportion to the frequency. That's inductive reactance, XFL. Inductive reactance equals 2 pi times the frequency times the inductance, ANCE, measured in henries. So if you change the frequency, you change the inductive reactance. Therefore, the voltage must also be varied in proportion to the frequency, so that Ohm's law division operation yields an unvarying value of magnetizing current. Okay. Oops, let's see here. 3.3.0, braking methods. Injection braking. DC injection braking occurs when DC is applied to the stationary winding of an AC motor after the AC voltage is removed. So you've got an AC motor and you've got alternating current being applied to the stator. And you turn that off, disconnect it, and then for just a split second, you put DC onto that stator. And what happens is you create a north pole and a south pole. And as that rotor is rotating, it has north and south poles. And when that south pole grabs the north pole, it sticks right there. So it's a very quick method of stopping that motor. This is an efficient and effective method for stopping most AC motors. DC injection braking provides a quick and smooth braking action on all types of loads, including high speed and high inertia loads. In an AC induction motor, when the AC voltage is removed, the motor will coast to a standstill over time because there's no induced field to keep it rotating. Because the coasting time may be unacceptable, particularly in an emergency, electric braking can be used to provide a more immediate stop. By applying a DC voltage to the stationary winding when the AC is removed, a magnetic field is created in the stator that will not change polarity. This constant magnetic field in the stator creates a magnetic field in the rotor. Because the magnetic field in the stator is not changing in polarity, it will attempt to stop the rotor when the magnetic fields are aligned. When the fields are aligned north and south, the two magnetic fields are attracted to each other. Resistive pull of the fields is used to stop the motor's rotational inertia. The same is true when the magnetic poles are the same, but instead of attraction, the magnetic forces repel one another, causing the motor to slow. And what happens is as soon as that rotor stops rotating, it's no longer cutting lines of flux, so there is no induced voltage or current or magnetic field in the rotor. So as soon as it comes to a stop, the rotor kind of shuts down. Stopping time is based on the amount of DC applied. Normally, the applied current is 3 times the full load current of the motor. The higher the current level, the faster the motor will stop. For instance, in paper mills where sudden motor stopping time is an issue, the applied current is less than normal to avoid tearing the paper. All right, dynamic braking is the highlight. Dynamic braking is achieved by reconnecting a running motor to act as a generator immediately after it's turned off, rapidly stopping the motor. That's what they do in the cars when they want to recapture that power. They can turn those motors into generators and they can recapture it. It can go back into the battery system. The generator action converts the mechanical energy of rotation to electrical energy that can be dissipated as heat in a resistor or used as a load as in a generator. Using the motor as a generator is not only practical, since the motor stopping time is very limited. Dynamic braking of a DC motor may be needed because DC motors are often used for lifting and moving heavy loads that may be difficult to stop. For example, forklifts often use dynamic braking. There must be access to the rotor windings to reconnect the motor to act as a generator. On a DC motor, access is accomplished through the brushes of the commutator. The armature terminals of the DC motor are disconnected from the power supply and immediately connected across the resistor, which acts as the load. Okay, let's see here. Let's move on. Section 3 review. With a constant torque load, the horsepower. All right, I'll let you answer that one. When variable frequency speed control is used on a motor with nameplate rating of 480 volts at 60 hertz, the voltage to frequency ratio is. and when using a motor with dynamic braking? I'll let you answer that.